The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, folks. So last week we we first saw our first magic formula, which you've probably forgotten because it was a wonderful weekend. So I'll remind you. And then from there we will resolve the spider problem. And then we're going to look at something called the super magic formula. These are not official names. I made them up. All right? So please never, ever say these in public. Okay? But it's a useful formula. Okay. So last week we looked at, as I said, first of all we looked at angular velocity for the first time. For the first time. And in fact, everything before I mentioned angular velocity, you know, the stuff I did before I even mentioned angular velocity for the first time, the machinery I provided you is powerful enough to solve pretty much any kinematics problem because it's based purely on geometry. Angular velocity is a kind of a made-up concept that just simplifies the math. And it's kind of intuitive. Stuff is rotating, theta dot, multiplied by, you know, the lever arm, right, gives you a velocity. But you can see how it kind of slotted into place. So we introduced the angular velocity like this. We said the angular velocity of, in fact, I'll fill that in later on. Frame A with respect to frame B. And I wrote it as this. So help me write this. What is the English statement here? It is the angular velocity frame B with respect to frame A, right? Okay, so we saw that for the first time. Now, a little bit on the lore of angular velocity that you've seen in previous classes, before we plunge in any more. The first thing is, can a point have an angular velocity? No. Can a point have a velocity? Yes. Can a frame have a velocity? Kinda no. Because if a frame's rotating, different points will have different velocities. So yeah, a frame can have a velocity, but doesn't really mean much until you tell me which point in the frame you're referring to, right? Look, this thing is a frame. What's the velocity at any given point in time of the frame? Well, no, I need to tell you which point I'm referring to, right? So if I look at the corner of this guy, this corner, yeah, you can tell me the velocity at any point in time, right? But the velocity of the frame doesn't mean anything unless I give you a reference point. So points have velocities, frames have angular velocities. Good? Points have accelerations, frames have angular accelerations. Okay. So just to talk a little bit more about angular velocity, why is angular velocity a vector? Say it again, I'm sorry.
Cross product?
I guess. Well, I guess you could look at it that way. But I want something even more kind of, just very basic, hand wavy. More basic, yeah.
Has a magnitude and direction.
Okay, and why does it have magnitude and direction?
Like that. Oh, that's what I was going to say.
But why, how is rotation an angle, obviously rotation is, how can you add rotations? What's up with that? You know it. You've seen this in class, yeah.
Same math comes out, right?
Huh?
So the math comes out.
And that's right. And why is that?
Because then you can take the cross product with another vector.
Say it again?
You can take the cross product with another vector.
Okay. That's right. But let me ask you something. If I said, look, I'm standing at this, right? I'm going to rotate about my vertical axis and then do this. My hand's up here, right? But if I rotate my hand first and that did the same thing. But you know what I mean? Angles don't add up, right? If I change the order in which I add angles, they don't add up, right? So if I set 45 degrees up, and I'm going to rotate 45 degrees, my arm ends up here, right? Why is the angle adding up here, Ajay? Has something changed over the weekend? If I turn 45 degrees. Anyway, you know the point. If you add up angles, they shouldn't add up. Something happened this weekend and all my angles are adding up. Yep.
Can we rotate clockwise or counterclockwise?
Well, look, shouldn't vectors add up, right? Angles don't add up, right? So, yeah, clockwise and counterclockwise means, yeah, there's a plus minus to angles, right? But you know where I'm going with this? Yeah, I'll just tell you the lore. The simple thing is, angles don't add up, but infinitesimal angles do add up. You remember this? You did this in physics. I'm assuming you did this in physics. Okay? So if I rotate about one axis a certain amount, 30 degrees, and then rotate about another axis 30 degrees, right? If I reverse the sequence, they don't add up. But if I rotate about one axis like a tenth of a degree, and then rotate about another axis a tenth of a degree, and then I reverse the sequence, actually you come pretty close. All right? So it turns out that infinitesimal angles do add up. So while in general, rotation about different angles, right, it doesn't add, different axes doesn't add up, infinitesimal rotations do. And because angular velocity is d theta by dt, right, and it's a vector because it is about some direction, and there's a d theta here, it turns out that angular velocity is in fact a vector in the sense that there is an axis, the angle is about that axis, and if you have another angular velocity, you add them up, they do add up. So the math does work out. You understand? Am I making sense or not making sense? Any questions about this? Anyone? Yeah. What I mean by angles don't add up is that if I said rotate a rigid body, right? Take this rigid body, and we have two rotations. One is about this direction, right? I was a little quick because I assumed you'd seen it before, but I'm noticing that you haven't seen this before. Perhaps they don't talk to you about this in physics anymore. So maybe let me take a step back and describe it in more detail. Let's take this rigid body, right? This is the z direction. Let's call that x, y, and z. So let's say I'm going to rotate it about z, 90 degrees, and then I'm going to rotate it about x. X is this, right? So it ends up like this. So remember this, it was facing you, right? I started like this, z, x, so it's facing you. Now instead, if I said rotate it about x first, and then rotate it about z, you understand? So if I just took theta as a theta with this vector, and I said apply these two rotations, well, depending on the sequence in which you added the rotation vectors up, you end up with a different position, right? But vectors don't have the problem. When you add two vectors, it doesn't matter what sequence you add them in, right? If I have two vectors, whether I do this, or whether I write this first and do this, the net vector is the same. You get it? So if I'm going to treat angles like vectors, they should add up, correct? Regardless of sequence, they must give the same result. But they don't. But it turns out that here, if I take a very tiny rotation, not 90 degrees, but like 0.1 degrees, and then 0.1 degrees, then the sequences do actually add up. Okay? And this is the sort of thing you need to kind of walk around with a book, and people will think you're nuts, but do that. And you'll see that the angles kind of do add up. You get it? So that's why when you take small angles, they do add up. And angular velocity is a measure of the rate of change of angle. So it's a d theta. It's a very tiny angle, get it? In a moment of time, right? In a very tiny moment of time. So angular velocity does add up, so you can treat it as a vector and the math works out. In answer to Sam's comment, okay? So what that means is, and this is what I wanted to tell you, if I have one frame A, another frame B, and another frame C, so let's say this is frame A, right? And I'm frame B, I'm going to rotate. Okay, and as I rotate, this thing which is frame C, which is moving on me, right? Then A omega B is my angular velocity, right? What's the direction? This way. That's frame A. I'm frame B. I'm rotating. What's the direction? Upwards, right? Straight up. So that's A omega B. Is theta dot this way, and the vector upwards. But now let's say that I'm moving this. What's the vector here? This way, right? Depending on the direction, this way or backwards, right? So here's the deal. A omega C is equal to A omega B plus B omega C. And this is what I wanted to tell you. And the beauty of this is that if you can identify between two frames an angular velocity, right, then, and between two other frames, and you can create a sequence of frames, you can calculate the angular velocity of the final frame. So if you look at a really complex system, a gimbal assembly, for example, right, you can always find little joints, right? Mechanical engineering is full of these, 1 degree of freedom joints. We call them hinges, for example, right? We call them, axes. And you can always add up the angular velocities, and the net angular velocity is the angular velocity of the final frame with respect to the first frame. And that's a very beautiful thing, which means that with this, we can take really complex situations and break them down to pairs and analyze the heck out of them, add them up, and you can get the behavior of that final, in terms of that initial frame. Get it? And maybe. So we introduced the velocity, and then the next thing we did in the last class was I revealed to you this magic formula. I said, if you have a vector, let's call it n, and you want to take its derivative with respect to the frame A. Now, the way we did it was we would rewrite n in terms of the basis vectors of frame A, right? In terms of A1, A2, it's a lot of math, a lot of derivatives. That's how we did it. And actually, it was Andrew who asked. He said, isn't there a nice way to kind of simplify the derivatives? Here it is. If it turns out it's more convenient to take the derivative of that vector in B, then you can do this. But you need this correction term, which is very beautiful. Done. Okay? So this was the magic formula that I introduced in the last class. How would we go about proving this? Anybody? Yeah, do the math. How would we do the math? How would we prove this? Here's what we'll do. Let's prove it. Let's consider a frame A. By the way, you notice I will always show frames with this little circle A saying that it's a frame, and with a little wiggly line pointing to it. I will always do that. If I don't, stop me and make sure I do it. Okay? Let's say there's a frame B. So frame A, for example, could be the projector. Frame B could be a transparency sliding on the projector. Got it? Now, you can always assume if I have a capital A that little a1 and little a2 are the basis vectors. Okay? Or the unit vectors. You can always assume that little b1, little b2 are the basis vectors in B. I'm going to stop writing it because it just clutters up the diagram. Now, let's assume I have a vector, let's call it n, and that it's given to us for some reason, naturally. For example, maybe it's fixed in frame B, maybe it's a spider walking away from the center of frame B, which is the frisbee, whatever. let's assume that you have a vector written in terms of frame B's unit basis vectors. Let's assume n is equal to sum u1, which is not a constant, times b1 plus u2 times b2. Now, what I'm trying to prove is this formula. How would I go about doing it? Someone, wake up. Everyone's asleep. Wake up, wake up. Yeah, let's express, exactly. We're going to express B. So here's what we're looking for. We're looking for A d by dt of n. And look, n is expressed in terms of b1 and b2. That's really not nice. We need it expressed in terms of a1 and a2 to do it the old way, the long way, right? So the way you would do it is convert it to an a1 and a2 representation. Can you please look at your notes and tell me what b1 is in terms of a1 and a2? Quick, look at your notes. Say it again. Is it plus or minus? So b1 is cosine theta a1 Is that right? Everyone in agreement? Okay, good, excellent. Plus u2 sine, it's actually minus sine theta a1 plus cosine theta a2, all vectors. Okay. I need to, sorry. Sorry. Okay. Yes. I'm going to finish that down here. So, could you please expand it for me? What does that come out to be? This is the left-hand side of that formula, right? And we'll do the right-hand side separately and show that the two are the same. I'm trying to prove it to you, right? So I'm not, I'm doing just very boring stuff, but we need to do it just to establish it. What is, expand it for me. What is d by dt of u1 cosine theta? It is u1 dot cosine theta, right? Minus u theta dot sine theta. Okay. And on the right-hand side, it is the next term. That's this term I just wrote. This term comes out to be u dot sine theta plus what? Theta dot cosine theta. I'm bunching the terms separately just to get the A1s all lined up, all right? So this is A1, and this is A2, all right? Okay, and then let's do this term. Minus what? U2 dot sine theta minus U2 cosine theta and below, what do I get? Mm-hmm. I'll put theta 1 here. This should be a theta dot, right? Yeah. Okay. So these are the terms. Any simplification? Does anything cancel out here? I should, shouldn't I? So is this 1 or 2? 1. What is this? This? 1, 1, 2. Okay. Is this correct? Okay. And does it simplify? U1 dot cosine theta, U2 dot sine theta. No, it doesn't simplify, right? And so this is the left-hand side. U1 dot. Okay. Now, is there some scope for us to rewrite this in terms of B1 and B2? Is there some scope to write this in terms of B1 and B2? What is U1 dot A1? What is A1 cosine theta plus A2 sine theta? Huh? B1. Uh-huh. So this is U1 dot B1. What else? This is B2 plus U1 theta dot B2 plus U2 dot B2 minus or plus? Huh. Okay, so that's the left-hand side up there. Okay? Any questions about this? You can even ask me, Sanjay, why are you doing this? Go ahead, you can ask me that. Thank you. I'm doing this because I want to show you that that magic formula is simply a compaction of a lot of math. That's it. Okay, so I'm going to write it out brute force, take derivatives using geometry that you understand, and show you that you get that formula, and it really works. So that when you use it, you don't feel uncertain. That's it. Okay. So this is the left-hand side up there. Now let's compute the right-hand side up there. What would so the right-hand side would be to take U1 B1 plus U2 B2 and take the derivative with respect to frame B, right? Yes? Maybe, right? So tell me what it comes out to be. What's the first term on the right-hand side? B2. Let's see if these terms show up there. Do they? Aha, yes, this shows up, this shows up. So this matches, right? So now let's take A omega B. What is A omega B, folks? Quick. Theta dot, it's a vector, B3. Isn't it theta dot A3? Why is it theta dot B3? They're the same. What if they're not the same? Well, here's the deal. By the definition of angular velocity, if you can define an angular velocity between two frames, there's got to be one axis that's aligned. Get it? Okay? So that right-hand side term, and we're going to use B3 instead of A3 just because our math's going to be simplified, right? So the right-hand side is going to be theta dot B3 cross product with U1 plus B1. B1 plus U2 B2, sorry. Right? And if you do the math, does it come out to be these two terms? Yes or no? Yes? So if you do the math there, I'm not doing it because I want you guys to stay awake in class. I don't want to just blindly copy down the notes here, right? So it all works out. Okay? I will never ask you to prove something like this in an exam. Right? This is almost like a solved example. I want you to understand that it all works out. That's it. And if you're confused, that is fantastic because that's a symptom of something else. And I'd like to surface it and help you figure it out. Any confusion about this? Anything? Yes? Claudio, right? Claudio. What's your name? John. Oh, sorry.
Just go over how you got that last term in there again.
Say it again?
Just go over how you got that last term.
This term? So look, what's the magic formula? It is the left-hand side is this, is equal to B d by dt of n, right, in the B frame, plus this correction term, right? So the first term here was bd by dt of n. The second term is simply that this guy. Make sense, John? You convinced? No. Are you convinced?
Convinced enough.
Okay. Anybody else? You've totally got to get this, Andrew, yeah.
So if you had a sphere rotating and you want to insert a gel in one plane and then a plane that was fixed, how do you actually describe the rotation of the sphere in terms of like the frame, the other frame?
Okay, let's do that. So let's imagine I'm spinning a basketball on my finger. I could never do that, but let's just imagine I'm doing it, right? I'm standing at this and spinning a basketball on my finger. The room, the world, the earth is a frame. The basketball is another frame. The kind of the, you guys need to be like Neo in Matrix. Have you seen that movie? Yeah. Right? It's very, very important if you understand matrix algebra. You need to see Matrix, all right? So you go see Matrix, and you know how Neo kind of, when he's totally, after Lawrence Fishburne's, kind of trained him, etc., he goes down and he can see. He stops seeing buildings and he sees these characters, flowing instead of the building, right? He sees right through all this, the video game, right? So similarly, what others see is a basketball spinning. What you see once you're done with this course is you will see an embedded basis frame, with its arrow, pointy arrows sticking out of the basketball. Get it? And you will see it spinning. Do you see it spinning? You see it, right? But one of the axes, which is the one pointing up, ain't spinning, right? It remains vertical. Got it? And you can kind of do this freeze frame where you freeze it, then a second later you freeze it again, you measure the angle, and that's delta theta over delta time. So you get angular speed, and the vertical axis is frozen. Get it? So you get that the angular velocity of this basketball is upwards. Is my hand waving? Are you following me here? Can you see it, right? Anyone not see it? It's basically all I'm saying is that here's me. This is my finger. Right? Here's the basketball. Okay. My hand. Here's the basketball. It's spinning. What you guys should see is these embedded vectors, basis vectors, sticking out. So you'll only see kind of the surface, sticking out, right? And then you see these two rotating like that, right? But that guy's stationary. And so in your mind, there's an angular velocity that that basketball has with respect to the ground. Got it? Now, if I was spinning it this way, which I couldn't because of gravity, but let's say that it was at a different angle, you can always introduce a frame on the Earth such that everything lines up, right? You just want to pick a frame and be done with it. Okay? Any more questions about this? Very important. Hey, let me ask you another question. When I say a frame is rotating, this is a tough one. So let us say there is a frame rotating with respect to another frame. Is it rotating about a point? Or let me put it differently. Is there such a thing as angular velocity about a point? No. Who said that? That's right. That's right. But if you think in your mind you can't understand why an angular velocity isn't about a point, look, I'm rotating. Is there an angular velocity about a point? If you think there is an angular velocity about a point, right, then I can understand that, but I want to talk about it. How many of you kind of feel there should be a point about which there's an angular velocity? Right? Come on, say it. I know I felt that way. You can admit it. Good, right? I felt that way. When a frame rotates on another frame, for an instant, with respect to that other frame, there might be a point that does not move. Get it? That is called the instantaneous center of rotation. But the angular velocity isn't about that point. It's the angular velocity of the frame, because the instantaneous center might move, and with respect to another frame that's translating, it might be some other point, right? Get it? So look, if I do this, if I'm spinning it, the center is staying stationary. So that is the instantaneous center of rotation. But this frame, there's no kind of special point, because with respect to someone who's flying overhead with a constant velocity, the instantaneous center of rotation is going to be some other point. The frame has an angular velocity. It's not an angular velocity about a point. Get it? So you need to dispel that. If you have that confusion, try and think about it. There is no such thing as an angular velocity about a point. It is an angular velocity of the frame, period, end of story. Just so happens that with respect to some other frame, there might be a point which is instantaneously not in motion. And that's the instantaneous center of rotation. But that's just a special thing. It's just the eye picks that up. But that's not fundamental. Okay, so that's angular velocity. So here's what I'm going to do now. I'm going to solve our old problem, spider, the spider on the frisbee, using your Claudio, right? Yeah, okay. Using frames, using angular velocity. So the problem was, we have the ground, we have the spider, the frisbee. We put a frame here. We call this point O. We call this P. The spider is some distance away from the center. We call that point Q. Now, I want to make another editorial comment here. We call this length L. We said this distance is U, and this distance is V. The editorial comment I wanted to make was, and this is very informal, I'll formalize this later on. How many degrees, assume 2D, all right? Assume this, it's like a hockey puck, it's sliding around the ground. How many degrees of freedom does the frisbee have?
Wait, are we looking in 2 dimensions?
In 2 dimensions, I have a frisbee, and it's, I'm throwing it on a flat plane, right? How many degrees of freedom does it have? 3. Okay. How many degrees of freedom does the insect have? In the same plane. In the same plane.
Can it depend on the frame?
What was that?
Can it depend on which frame you're looking at it?
Well, I'm just asking you, how many degrees of freedom does an insect have on a plane?
2 is a point. Or are we treating it as...
Treat it as a point. Okay? It's treated like a dot. It's only 2, right? But yet, we characterize this situation with 3 parameters. Okay, and the parameters are the positions of the center of the frisbee, right? And the distance of the spider and the angle of the spider from the center of the frisbee, right? And assuming the spider is only moving in a straight line with respect to the frisbee away, then we just need a distance, right? So what we're doing is we're saying those are the 3 parameters that change in our geometry, and with those 3 parameters, we're going to capture the location of the spider. But we're using 3 parameters. But in the end, the spider is only going to have 2 degrees of freedom, right? But that's okay, because when we get the velocity of the spider, it'll have only 2 components. When we get the acceleration, it'll only have 2 components. So it'll work itself out.
What are the 3 parameters?
The 3 parameters are U, V, and L. The way we're doing our geometry, we're saying the spider, look, this is just informal, okay? I'll formalize this later on, right?
What about theta?
Actually, that's right. We're using 4. Thank you. We're using 4. Thank you. I forgot about theta. Thank you, Ted. Right? We're using 4 parameters. Right? But in the end, that insect can go right or left or up or down on the blackboard, right? So it has only 2 degrees of freedom, the insect. But we're using 4 parameters to capture this whole system. And the reason is that we need to capture the location of the spider, but we also need to figure out where the frisbee is so that we can do the math with respect to the frisbee, etc. Right? So we're capturing it in terms of these parameters. I just want to say this, leave it for the time being. We'll come back and I'll, in the context of dynamics, it'll become more clear when we talk about degrees of freedom and parameters and things like that. It'll all become more clear. But I just want to say this. The parameters are the things that change. Okay. So how do I use the magic formula to find the acceleration, the velocity and acceleration of the insect? Anybody? How do I begin? Write down the, always begin by writing down the position vector. So R, O, S is equal to U, A1 plus V, A2 plus L, B1. L is the distance of the spider from the center of the frisbee. Oh, I call that Q, sorry. I'm sorry. Q. Say it again. Let me ask you. When I write a position vector, does it need a reference frame? Doesn't. The only thing where I can get away without writing a reference frame is when I write a vector. A vector is just, the frame when I write a vector is implicit in the basis vectors. Get it? I don't need to say it's with respect to A or with respect to B. It's just a mishmash of little vectors that are all defined in terms of parameters. It's an important question. You need to understand this. This actually encapsulates the geometry of this entire problem, right? Because if I change U1, the whole thing is going to move to the right. If I change U to if I change U, the frisbee is moving to the right. If I change V, the frisbee is moving up, right? If I change theta, the whole thing is rotating because it'll change B1, right? If I change L, the spider's running away from the frisbee. Okay. By the way, if you ever end up in video games, writing video games, graphics, etc., this is it. This is how you do graphics. It's the geometry of points, right? So imagine you were writing a video game where you had a spider running around a frisbee, right? And maybe and the frisbee is, flying about, and you want to write a video game where you want to put a bigger spider and you want to chase the spider towards the middle, whatever, right? The geometry would be this. This is how you would do it. Get it? So think video games. Kinematics is video games, actually. Okay? And when you change the parameters, things change parametrically. That's also called parametric design. Okay? Okay, so how do we solve the problem now? I want both the velocity and acceleration of the spider. Quick. Take the derivatives, right? So the velocity of the spider is Q, I called it Q, vector. So A being a derivative, I need a frame, is equal to A d by dt of this vector, which is, now these two guys, no problem. I can write them as U1 dot A1 plus V dot A2, not U1, U2, but U dot V dot, right? Plus, now I have this kind of mismatched term where I'm taking the derivative with respect to A, but I have this vector expressed in terms of the B1 basis vector, right? Before, I would convert it all to A1 and do the math. Today, now, with the magic formula, we can rewrite this as what? So, first of all, L is a scalar. So there are a couple of routes we can go here, okay? And I just want to give you the routes. One thing we could do is we could say L dot A by dt B1 plus B1, we can kind of do it that way. But the simpler way to do it is to it doesn't matter. We can just write this as B, take the whole term, d by dt of LB1 plus what? Quick. I'm hearing a hesitant murmur, not the "Rrr." Yeah. I was mumbling something a moment ago. I'll tell you what I mean. What I was trying to say. Cross LB1. What is A omega B? So we can rewrite A omega B as theta dot B3. And so this whole thing comes down to, I'm going to write the answer here to save a blackboard. What's the answer? What is AVQ? What? Which is the answer we got before as well, right? Now what I was mumbling, I started mumbling in the middle of the class. I do that often. I also drool, but that's okay. What I was trying to say here was you can go a couple of ways with this, right? You can say L is a scalar and pull it out and just apply this whole thing to, do use the chain rule. Or you can just treat the whole thing like one vector. Get it? And they're both okay. They'll both come out to the same answer. That's okay. Okay. Because L is a scalar, you can just, L doesn't care which reference frame you take the derivative in, right? Doesn't care what a reference frame is. B1 is a vector. It cares which reference frame you take its derivative in. L doesn't. You understand? So you can do this by parts. By chain rule, and say L dot, L dot B1 plus L A by dt of B1. Whichever way you do it, the answer will come out to be the same. Just go naturally. Understand the basics. Go naturally. It'll work itself out, is my point. All the rules apply. Okay? All right, so now we want to calculate the acceleration. Now we want to do the acceleration. Bless you. How do we do this? Come on. Say it again. Yep, take the derivative again. So we're going to take the derivative of this guy, right? I'll just write it all out and we'll do it neatly this time. D by dt of u dot A1 plus v dot A2 plus L dot B1 plus theta dot LB2. That's what we're taking the derivative of. The first two terms are easy. It's going to be u double dot A1 plus v double dot A2 plus, what do we do now? Come on, someone back there. Huh? Magic formula, right? And so the magic formula, the way it'll come out is, this is going to break down to two terms. The first term is it's going to be b d by dt. Sorry. It's going to be two terms. The first term is b d by dt of b1, of L dot b1, plus a omega b. I'm going to stop writing a omega b. I'll just call it LB3 to save ourselves. Sorry, theta dot b3 cross L dot b1. So these are the two terms from this guy. And what do I do with the next term? I repeat it. So I'm going to get b d by dt, bless you again, yeah, theta dot L b2 plus a omega b, which is theta dot b3 cross theta dot L b2. Is that complete? Have I missed any terms? Anybody? I might have, on purpose, by mistake. You never know with me. I think it's correct. Okay, and that is u double dot a1 plus v double dot a2 plus, this is going to be easy now, it's going to be L double dot b1, and this is going to be what? b2 plus, this is, now we need to do this guy using a chain rule, right? Because the two terms you have to take the derivative of, right? Say it again, I'm sorry?
L dot.
Oh, L dot. Here? Yeah. So here what do we have? We get theta double dot LB2, L dot B2. So by the way, you notice this term showed up twice. Why? That will become, so anyway, we'll remember that. Plus what is this? And let's summarize this. And you have to admit, wasn't the math much simpler than the first long way, right? Because we used a trick. We compacted the math recognizing the magic formula, right? And it was all initiated by Andrew, who asked the question, why don't you do it, right? For which he gave up his watch. Jay, I'm going to show the videos now, okay? Just to kind of break the monotony and proverb. Start with the merry-go-round, and then the other one, right? So this is it. I'll tell you when to start. On this one, right? Okay, I'll tell you when to start in a second, right? So these are all the terms. They're going to be, there should be 1, 2, 3. Did we miss anything? Oh, we missed something for sure. Yeah. Okay, now help me, remind me what these terms are. What is this guy? Translational acceleration. What is this guy? Spidey's acceleration with respect to the frisbee. What is this guy? Yes. And you'll notice with Coriolis, these two terms always show up in different places, and they add up, and that becomes 2, right? What is this guy? Centripetal. What is this guy? It's called Euler. Whatever. Okay. If you, as I said, if one of you invents a new term, we'll name it after you. Okay. And so far I've used these words, Coriolis and all that. I've kind of called them out without telling you a lot more about them, right? So what we're going to do now is take a break in the following way. I'm going to pull down the screen. I'm going to show you some videos showing you the Coriolis force. When we're done with these videos, you will A, totally understand what the Coriolis Coriolis acceleration is, and B, have a headache, right? And then we're going to go back and do the super magic formula, where we actually lay these things out. We're going to derive a very general formula for something moving on something that's moving. Get it? No, seriously. It's going to be a general formula. You see, all the formulae that you have so far are for something moving on a frame, right? But now we're going to but this frisbee is something moving on something that's already moving. So we're going to come up with a general formula for that. And for the lack of a better term, because it doesn't have a name, I named it the super magic formula as a code word in this class. So it turns out that several people have done research, and I mean not like hardcore technical research, but research involving merry-go-rounds, bowling balls, billiards tables, and a lot of courage on the use of, on demonstrating the Coriolis effect. And these videos, if we can get them going, are actually very, very interesting. Okay. And what you'll see, by the way, here, okay, just 1 second, Ajay, before I set it up, right? I just want to set it up. So these are 4 kids. They're sitting on a merry-go-round, and then someone comes and starts spinning the merry-go-round, right? There are 2 cameras. There's one camera outside that is attached to the earth looking down. So what you see from above is what really happens in an inertial frame, right? Which is things want to go straight. But the kid in the merry-go-round sees something different. Go, Ajay. Volume turned up?
To an observer above the merry-go-round, the path of the ball appears straight.
Isn't it straight?
While to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis force.
I think one of the kids fell off.
To an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
Get it? Kinda, got it? Kinda? All right, let's do the other one. All right, so this one I discovered, I think last night. And there are 2 dudes who went to a high school, and they put a billiard table on top of the merry-go-round. Okay? And then they did some experiments. And these are very committed people, I must say. It's obviously also a cold day. And I just thought I'd put it up just to show you the power of human innovation. Go ahead. But these dudes are totally into it, so they don't stop. But the funny thing is that the kids actually can't see all this because they're below the level of the pool table. So they're like jumping up, you know. Okay, so let me explain what's going on here. So it turns out, and then we're going to do this super magic formula in about a minute, right? It turns out that with respect to someone standing in space and not rotating with the planet Earth, right? So if you're standing above the North Pole and you're looking down at the Earth rotating, it's like a merry-go-round, right? A particle of air which is moving for one reason or another. With respect to me, it's going to move in a straight line. But to people sitting on the Earth, because they kind of move, rotating away, they're going to see it kind of swing away. Get it? And what happens with things like hurricanes, and I'll show you some videos later if we have time, is so now you're on the North Pole, right? You're sitting on the North Pole, and this is the Earth. This is the North Pole. Okay, you're looking down. A particle, when it's, let's say there's a low pressure, right? Let's say there's a low pressure region here. Low pressure. So when all the particles start rushing towards it, because it's low pressure, right? But they think they're going in a straight line. But meanwhile, this guy, right, is attached to the Earth, kind of, moving with the Earth. So with respect to us, the particle kind of veers off to the right. Get it? And then it collapses into a spin this way. And that's why hurricanes and tornadoes and stuff like that, that's why it spins in a certain direction in the northern hemisphere, and the southern hemisphere spins the other way. Right? Because the particles can rush in, and then they veer to the right. And then they get sucked in this kind of rotation. So you've probably heard about sinks, right? About toilet bowls and stuff like that, and how the water rotates in one direction in the northern hemisphere, another direction in the southern hemisphere. Is that right? Is that valid? Yes or no? Why not? Yeah, it turns out that in that scale, in fact, there is a Coriolis effect, but the slight deviation angle is so slight, it's like fractions of a degree per meter at that scale, that it doesn't build up enough to really impact the direction in which the vortex takes place. Okay? The vortex is created far more by asymmetries in the sink or by rotation that was created earlier that kind of remained. Okay? The angular momentum, which we'll cover later on in the class, it stays for a long time, and it influences things to go in one way or the other. So with sinks, in fact, you can construct a really large sink, and apparently you can show it, but it's very hard to do it. It's very hard to kind of isolate environmental factors. So sinks, not a valid example. Hurricanes, a valid example. Okay? So do you get a sense of what the Coriolis effect is? And remember, the Coriolis effect is this guy, and we'll now formalize it. When something is moving, that is translating with respect to a frame which is itself rotating. In other words, there's a theta dot and an L dot term. Get it? Then there is a deflection in the B2 direction, in the way we've written it. Now I'll give you the general formula, and B2, what it is, etc. will become more clear. Any questions about Coriolis? By the way, in the last class, I told you this anecdote. I said that artillery guns, right, in the 1700s, 1800s, they would have to compensate for directionality because of the Coriolis effect. It turns out that that is true, but I made one mistake. It turns out that when the Coriolis effect was discovered, or when someone formulated it, Coriolis, right, the range of guns wasn't high enough for that to have been, really valid. So it is true that in artillery you need to correct for the Coriolis effect, but that wasn't the reason the Coriolis effect was discovered. So I take it back, right? But it is also true that in World War I, when a British fleet near Falklands ran into a German fleet, they shot 1,000 shells, taking the Coriolis effect of the northern hemisphere while they were in the southern hemisphere, and missed. And then 60 shells, they actually used the right correction, and they nailed the German fleet, and they won that battle. So it's certainly true that by the time World War I came along, the range of these guns was high enough that the Coriolis effect was relevant. But I take back my earlier statement that it was the motivation. I believe not. Any questions about this? Anyone? Any comments? Like the video? You want to see more videos like this? In fact, why don't we just watch YouTube videos all day? It'll be fun, right? All right, what I'm going to derive now is a general formula for something that is moving with respect to something else, which is also moving. And this is a very common thing. A ship is moving, and someone's moving on the ship. A spaceship is moving, and an astronaut's moving on the spaceship. What is the force that the astronaut feels? You know, or what force must the astronaut exert in order to move in a straight line with respect to a spaceship or a space shuttle or something, given that the space shuttle itself isn't moving in a straight line? That's the question we seek to answer. And what we're going to do is basically generalize the frisbee problem. And the way we're going to do it is like this. We will define as usual. And you'll find this all repetitive because really it's all the same stuff over and over again, just getting more and more compacted with more insights kind of teased out of it, right? And we're pretty much done with kinematics once we finish this concept. It's beautiful. And now, by the way, this kinematics that I've done is completely 3D, right? You can do any 3D system with this stuff. In fact, the way that we're doing kinematics is called the Kane's method of kinematics. Kane, K-A-N-E, is a professor at Stanford. I think he's still there, retired. Kane's method is used to analyze the dynamics of robots, complex robots, and space systems. So anyone who works in, complex astro space system things like space shuttles with robots moving around, etc., they use this method. They use the symbology, A, B, and all that, right? Very few undergraduate courses on the planet teach the mechanisms that you've learned and understood, right? This is it. That's all there is to it on the kinematic side. Now, Kane also has a way of doing dynamics, which I won't tell you. I'll do the Newtonian approach. But certainly on the kinematic side, you've got it. OK. So the problem we seek to solve now is A. You have frame A. I'm actually trying to derive a general formula that captures what we did for the frisbee. You have a frame B. And what we're going to say is frame B is hurtling through space. And frame A is our ground reference frame. OK? And in frame B, let's assume that this is point, what did I call it in my notes? P. And this is point Q. So I'm just generalizing it. Earlier I put that, the spider was going along the B1 basis vector, right? So I'm just generalizing it. So now there is a point here. And that point Q is moving. It's moving with both with respect to A and with respect to B. But we want to express the acceleration, the velocity and acceleration of point Q with respect to frame A, assuming that it's more convenient to naturally denote it in terms of frame B. Get it? Like I'm walking in a spaceship. I can measure my distance to the back of the spaceship, right? But I really want to calculate my acceleration with respect to the Earth. OK? So that's what we're trying to do now. OK. So this is R PQ. And we'll call this point O. And this is R OP. Okay? And what we seek is the acceleration with respect to A of point Q, sorry, the velocity, and the acceleration with respect to frame A. This is what we seek. And it's just a generalization of stuff you've done now several times. OK, so let's write it out. So how do we begin? We're looking for these two guys. How do we begin? Position vector. Always. Yes, correct. R, O, Q. Now, I'm going to compact things and go a little fast, OK? Is equal to? Expand it for me. I'm going to have to Well, I'm just trying to calculate our AVQ, which is the derivative of this. And what do I do? I'm actually leaving it a little unstructured because I want you to say something. The answer I was looking for was, what is the derivative of our OP, Claudio, with respect to A? What do we call that? Say it again? It is, yes, it is. If I take the derivative of this, it is, right? Plus the derivative of this. So in fact, if you want, I'll expand it. I'll write it in smaller steps so you can follow it. Right? I've just written it out. Right? And what I'm saying is, this term you will recall is what? I just wrote it. And what do I do here? Apply the magic formula, right? And I can write this as B d by dt of R PQ plus A omega B cross R PQ. Right? Just applying the magic formula. And the reason I'm doing that is I'm going to reduce it to a simple form, which is A VQ is equal to A VP plus B VQ. Isn't this BVQ? Plus A omega B cross RPQ. So this is the velocity version of the magic formula, and I'm sure you'll admit that I did nothing particularly profound in deriving this. Okay? And in that handout, the typed handout that you hopefully downloaded and read from the web, you will see this expanded out for you. Okay? So that means that if you have a frame A, which is stationary, for example, you have a frame B, something's moving on frame B, then the velocity of that thing on frame B is simply the velocity of a point on frame B with respect to frame A, velocity of that thing with respect to frame B, and omega times R, basically. A omega B cross RPQ. Makes sense, right? Questions? It's obvious, nothing profound. Okay. Now, so this we've done. I'm going to do this now. So if I want the acceleration of point Q with respect to frame A, what do I do? Yeah, just take the derivative of that one. That is equal to A d by dt A VP plus A d by dt of BVP, right? BVQ, I'm sorry, plus A d by dt of A omega B cross RPQ. Right? I just wrote it out again, boringly. I strive to be boring at some level. If I'm doing anything that's not boring, that means I'm making a leap that is not grounded. Yep. Did I miss something? Yep. Yeah.
Point of clarification.
Yeah.
P is actually fixed in frame B.
P? Just so you know, thank you, Ajay, that point P is a point fixed in frame B. You understand? Very important. So, space shuttle, astronaut cavorting on space shuttle, find one point on the space shuttle. For example, the instrument panel that figures out where the space shuttle is, that's point P. Get it? So RPQ is that vector. Okay? Okay, so now let's do this. How do we expand this? What is this term? Come on. Yep. What do I do here, guys? Magic formula. So that, I line these two guys up, right? Plus what? What? Plus? So that's these two terms correspond to this guy. What next? What do I do with this guy? Same thing? Okay. Absolutely the same thing. That's correct. Precisely. Okay? Same thing. Okay, don't worry. It's all going to work out. This is perfectly kosher. I didn't do anything wrong here. I don't think, anyway. Did I do anything wrong? I just took this whole thing, boop, and I just applied the magic formula. Right? Yes? Anyone feel queasy about it? No? It's perfectly reasonable. Okay? All right. So now let's expand it. What is this guy? Yeah, very good. B. What is this guy? Well, it's just that. It is what it is. You will recognize it. Does anyone recognize what this guy is? It's half of the Coriolis effect. The Coriolis effect is actually two terms that come together, right? And it'll become two eventually. So we need to look for another of these guys. Keep an eye open, all right? Okay. What do we do here, folks? Tell me. Claudio.
Leave it as it is.
No, we don't want to leave it as it is. We want to expand it out. Take the derivatives away. Yep. What's your name? Yeah, what's your name? Sorry? Jeremy. Yeah, what did you say?
I was just thinking through omega, A omega B is saying theta dot. So you could say theta dot.
Yeah, but it's a vector. You're on the right track, though. Can you do it using the chain rule? Why not? Let's do that. Okay? Let's do this. B d by dt of A omega B right, cross RPQ. Okay. I have a caveat when I finish this. I'll come back to it. What I'm doing here is fine. Plus A omega B cross B d by dt of RPQ. So that's these two guys. Make sense? Plus, what about this? What do I do there? I just leave it as it is. Don't worry. Okay? Yeah. Okay. I can't change the order. Did I change the order? Yeah, you can't change the order. You cannot change the order. Say it again, I'm sorry? Aha. We'll come to that. Let's come to that. Okay, hold that thought. If it's 0, it'll go away. Okay, so just let's not expand it yet. So, and this term is just this term, all right? Okay, Ajay? Did I right? Okay. Ajay is kind of my guardian angel. If I make typos, right, he catches me. Ajay is a PhD student. He's getting his PhD in wireless sensing. Oh, sorry. Simone, I'll be out in a minute. One more minute. Huh? Just 1 minute, sorry. Thanks. Andrew, next time set your watch 3 minutes fast like mine, okay? So folks, I'm going to write out the super magic formula. Actually, this is it, okay? The super magic formula is this, and I'll name the terms and we'll finish it next time. A acceleration of q is equal to, read it out to me, please, is equal to the acceleration of point P, which is the fixed point, plus B a q plus aha. What is this guy? Alpha. Huh? Did I skip? Which term did I miss? Skip. We'll come back to this. Okay? This guy shows up as this guy. This is also, right? Plus what? Q. Yeah. Sorry. And plus this thing. Okay, we'll end now because Professor Socrates needs to take over. This is it. This is correct. Acceleration of P, acceleration of Q with respect to B, Euler, Coriolis, centripetal. And you know why it doesn't go to 0? Because I'm not taking A omega B cross A omega B. I'm taking A omega B cross this whole term, which is at 90 degrees to A omega B. Got it?